means the rate of doing work. 1 horsepower is required to raise 550 pounds, a distance of 1 foot, in 1 second. If 1 pound is moved through a distance of 1 foot, 1 foot-pound of work has been done. Therefore, 1 horsepower is the power required to perform 550 foot-pound of work per second. The unit of power in electricity is the watt, and 1 horsepower is equal to 746 watts. In electrical terms, 1 watt is the power expended when 1 volt moves 1 coulomb per second through a conductor. In other words, 1 volt at 1 ampere produces 1 watt of power. The formula for electric power is as follows: watts equals volts multiplied by amperes. The formulas are as follows: W, which is the watts, equals E, which is the voltage, multiplied by I, which is the amperage, and P, which is the power, equals E, which is the voltage, multiplied by I, which is the amperage. An electric current flowing through a conductor always produces heat. However, in most cases, the rise in temperature is not noticeable. The heat generated in a given circuit is proportional to the square of the current, as indicated by the following formulas. The formulas for finding watts or power when the voltage and amperage are known. W, which is the watts, equals E, which is the voltage, multiplied by I, which is the amperage, or P, which is the power, equals E, which is the voltage, multiplied by I, which is the amperage. The formulas for finding watts or power when the voltage and resistance are known. W, which is the watts, equals E, which is the voltage squared, divided by R, which is the resistance, or P, which is the power, equals E, which is the voltage squared, divided by R, which is the resistance. The formulas for finding watts or power when the resistance and amperage are known. W, which is the wattage, equals R, which is the resistance, multiplied I, which is the amperage squared, or P, which is the power, equals R, which is the resistance, multiplied I, which is the amperage squared. If energy is lost in an electric circuit in the form of heat, it is called an I squared R loss, because I squared R represents the heat energy lost, measured in watts. Knowing the relationship between power and electrical units, it is easy to calculate the approximate amperage to operate a given motor when the efficiency and operating voltage of the motor are known. For example, if it is desired to install a 10 horsepower motor in a 240-volt system, and the efficiency of the motor is 85%, to find the amps, calculate as follows. In step 1, calculating watts, the formula to be used is W, which is the watts, equals horsepower, multiplied by 746 watts. Therefore, W, which is the watts, equals 10 horsepower, multiplied by 746 watts. In step 2, calculating amps, the formula to be used is I, which the amperage, equals W, divided by E. Based on this formula, I, which is the amperage, equals 7,460 watts, divided by 240 volts, which equals 31 amps. Therefore, the calculated amps is 31 amps. For example, if the motor is only 85% efficient, and the current or amps must be divided by the efficiency to find the amps required to operate the motor at rated load, the calculation is performed as follows. In step 1, calculating efficiency, the formula to be used is efficiency equals A, which is the amperage, is divided by the percentage. Based 1 formula, efficiency equals 31 amps divided 85% efficiency, which equals 36.5 amps. Therefore, the amps, after applying the operating efficiency, is 36.5 amps. In the illustration, solve the exercise problem for finding watts when the voltage and horsepower are known. In step 1, finding known values, E equals 480 volts, and 1 horsepower equals 746 watts. In step 2, setting up formula, W, which is the watts, equals horsepower, multiplied by 746 watts. In step 3, applying formula, W, which is the watts, equals 20 horsepower, multiplied by 746 watts, which equals 14,920. In step 4, applying formula for amps, I, which is the amperage, equals W, which is the wattage, divided by E, which is the voltage. Based on this formula, I, which is the amperage, equals 14,920, divided by 480 volts, which equals 31.08 amps. In step 5, applying formula for efficiency, the formula to be used is, efficiency, equals A, which is the amperage, divided by the percentage. Based on this formula, efficiency, equals 31.08 amps, divided by 80%, which equals 24.86 amps. Therefore, the amps, after efficiency, is 24.86 amps.